And I think we are live with our first webinar. I can see we have most people signed in of everyone who registered. So welcome to all of you, and thanks for joining our first ever webinar session in in-situ Chips. So today we're going to try this out for the first time, and I hope to get some questions from you. I'm going to present some slides, and my partner Niccoló is going to present some slides. We do it one by one, and at any time during the presentations, you can see that there's a question tab in the bottom right of your screen. And at any time, you can just add questions to that if you have questions to the slides or anything in general, and we'll do our best to elaborate. So my presentation will probably be around 15 minutes, and Niccoló's will be about the same. So about 30 minutes, give or take in total. And then the added time for any questions you may have during. So I'll share some slides, see if it works. All right, slides are shared. All right, so what I will tell you about in my slides is the novelty of this nano channel chip and just briefly in the end what it can be used for. I'll also say briefly, we are a 3-year-old company in a few weeks and we are a growing team. You can see our team members here. I'm Emil to the upper left corner here, and Niccoló is the other person who will be speaking today. Niccoló is our industrial PhD and has done some very exciting work on the nano channel chips and got some results with that he will share with you after I'm done. So in-situ Chips is a company based off of a new technology, and that's why we have this motto, revolutionizing liquid cell TEM. The thing is, Christian, who is a co-founder in in-situ Chips, he started working with a traditional type of liquid cell for TEM. And we call these clamped chips because you clamp them together manually to encapsulate the liquid in between. And Christian was good at making these chips, along with others in his group, but he grew quite frustrated with a number of things. So, in order to combat those frustrations, he created the Nano Channel Chip. And just to mention some of these, we call them cons here, some of the things that frustrated Christians and other users that we've been talking to about this clamp chip system is membrane bulging. That means you have poor liquid thickness control. The thickness of this chip varies. In addition, it's hard to make quite thin liquid anywhere, which means your resolution suffers. It's also difficult to prepare, and you need quite a lot of practice to assemble it well. And once you do, it's somewhat time consuming. And being an open chip exposed to air and whatever environment it is in, you also have potential contamination issues. And when you have flow through the chip, you ideally want the flow to go over your particle that you're looking at in the TM, but it may also go around and you don't really have that precise control of where the flow goes. Also, the mixing you can do in these types of system is right before the chip and then flush in the mixed products. You can't do mixing right in the field of view where you want it. And finally, being difficult and time consuming to prepare, we have spoken to many users who typically only do one sample and one session per day, which means it's also a little bit of a slow throughput method. So the Nano Channel chip actually solves or at least helps these issues a lot, all of them. And the main novelty here is it's a monolithic chip. That means it's made in one piece. It means there's no assembly. All the channels are prepared like we want them, and we can define the liquid thickness very precisely, and it's very consistent. And the same we can do with the nitride membranes. In addition, it's also a superior flow system because the flow will go through the channel. It can't really go anywhere else. And it has 4 inlets, or rather 2 inlets, 2 outlets. So we have a 2 bypass chip system. The way it works is the chip itself has these 4 openings, 2 inlets, 2 outlets, and those are each sealed in the tip of the holder, the TEM holder, with O-rings. And then through the entire holder, leading onto the backside, you can access all these inlet outlets and actually flush in liquids very easily during TEM sessions. So to go through each of these pros and cons of the old system from Christian's group and the new system we made, we'll just start from the first one, which is bulging. You know, the bulging is an issue that we help with making channels. And if you can think of a quite wide channel, it's kind of like a clamp chip system. You have a wide membrane and lots of material to bulge when the vacuum outside pulls it outwards. But if you make that channel a bit narrower, you have a bit less material and therefore a bit less bulging. And if you make it very narrow, like we do, you effectively maybe start out with the same liquid thickness, but you maintain it even when there's a vacuum outside or an internal pressure in the channel. And you can see that here. The image to the left is an actual TM image of a water-filled nanochannel. And you can see the contrast across is indicating that there's no increase in liquid thickness in this channel. And then there's the precise control of liquid thickness. Here I have some examples from our recent batch of chips where we made this design of nanochannels. I should say the whole square you see here is everything exposed in the TM. All of this is transparent nitride, and all the colors are the channels themselves. So we can pack a vast amount of channels inside. This entire field of view is about 750 microns wide. But you can see, although it's the same design in all four cases here, they have different colors. And what you can do actually, due to refraction of light, you can see by the color about what thickness the channel actually is. And you can see how homogeneous the color is all across the entire chip. So all of these channels are about 60 nanometers deep. Then there's the assembly. And with the clamp chip system, you had to do it with your fingers, but with the Nano Channel Chip, you don't have to do it at all. We have already assembled the chip inside the clean room and bonded it together so it doesn't come apart, and therefore taken all the assembly out of the workflow. And as our customer Andy says, it only takes about 5 minutes to do. And that's whether it's the first time in the day or if you want to exchange samples throughout your TM sessions. And that brings us on to the higher throughput. We have Aaron here, who at his very first session was able to do 8 different samples in just over the course of a few hours. And then we have Patricia, who loads samples in a glove box because they are air sensitive, the samples that go in. Another point is that because it's bonded and sealed, it actually stays chemically clean until you use it, because each of the 4 inlets have a membrane sealing the inner channels, and you actually have to use a needle to poke it open before use. And that's the first time these channels see real air, or rather they've seen clean room air until this point that you rapture it open. So the channels stay extremely hydrophilic and extremely clean until you start your experiment. And regarding with flow control, you know, the channels direct liquid exactly where we make them. So you can see gold particles flowing through the channels here. And in this video, I use a syringe to stop the particles when they're in the middle of a channel. But with a syringe or with a pressure pump system, you can pull these particles back and forth in any number almost of velocities. They can go very fast as well, if that's what is needed. In fact, the channels have been tested up to 38 bars, so they can take quite a lot. And with flow, you can also do mixing. And we have 3 different kinds of mixing. In this video, you see a type of mixing where we create a gradient of 2 liquids as we exchange them one by one. Here is a fluorescent liquid, rhodamine, being exchanged with water interchangeably. And we also have this maybe more conceptually simple case where we just bring 2 liquids together from 2 different channels into one central channel. And finally, we can mix liquids by having them diffuse together. And we do that, for example, by having a long dead-end channel. In this video, you can see how it's full of a fluorescent liquid, in this case, fluorescein. And if we flush water through the very short dead-end channels to the left here, they get exchanged with water very fast. The mixing that takes place here is almost It takes only a few seconds. But in a longer dead-end channel, you can look at mixing regions here for many minutes, depending on how long you make this dead end. Let me just check if we have any questions. We don't yet. All right. So this brings me to the final pro-con, which is the resolution. Because we can control the liquid thickness and the nitride thickness so precisely, we can also consistently have high resolution, whether it's beam-sensitive samples like ettringite you see here, component of cement, or it's more robust samples like gold. We can get lattice fringes and diffraction spots in these samples as a complete standard feature of the chips. And in the end here, so now I've been telling a little bit about the chips, the novelty, and why we revolutionize liquid cell TEM. So I just want to end up highlighting a few results you can do. And this result is utilizing a temperature control feature that we have in our new patent pending solution, where we can heat the entire tip and all the liquid in it up to about 120, maybe 150 degrees C. And in this case, we start by filling the chip with supersaturated carbonate solution. And as we begin heating, we see the channels start to form these structures. And when we zoom in, we see they're actually crystalline. And in the end, we're able to get this lattice fringe image of the crystals actually grown live in the TM as we were doing the session. Another case use of our chips is in situ growth by mixing. So the other one was by heating, but David and Professor Ute Keiter from Ulm in Germany, actually our first customer ever, much appreciated. They were able to make atomic resolution growth of a MOF in situ. And they were able to publish this paper about it that you can find a link to on our website if you're interested in reading it. Another cool novel thing when you have the liquid thickness control is EELS and 4D stem, which does require fine tuning of the liquid thickness. And because we have this very uniform thin liquid, it becomes pretty much standard performance when you want to do EELS and 4D stem. And we were able to showcase this with Gatan, where we spent a week doing these experiments, not just the goal, that was just one day, but showcasing many new features of the system that becomes possible with the fine liquid thickness control. So to finish off, I'll reiterate that we and our customers, who so far have been quite happy customers, are saying that this system is very easy to use. Even some say it's the best experience and it's fantastic. And that's why we keep pushing the Nano Channel Chip technology and creating new features in it, new functions, and improving, hopefully to help more and more of you with your research. And with that said, I think I'll first off take any questions, if there are any. One just popped in. And after questions, we'll hand it over to Niccoló, who will present about some of his novel development. So we have the question here. We are asked from Yusra, what about beam sensitivity, polymer or protein-based samples? Can we get good contrast? Also, how about bacterial samples? They usually come in sizes as big as 1 micron. What's the size limit to get good resolution? All right, so a lot of questions here, but regarding the sensitivity, I think actually Niccoló has a little bit of results that you'll see soon about proteins. And I would say these very sensitive things are hard. So I would say we are right on the sort of borderline where it becomes easy to do. I think resolution-wise for protein, we're right on that borderline where we think we can see it, but we don't think it's too convincing yet. So what we're gonna do upcoming is we're gonna thin down the nitride even further. And I think that's gonna bring us into the domain where we can actually see proteins well. But we think we've seen it, so we're definitely very close. And regarding bacterial samples, it's a bit of a trade-off because yes, they can be big and we can make any size channels. So if we make a channel that's 2 micron, we can put 1 micron bacteria in, but your resolution in TM will be quite poor. And it's definitely not going to be as good for high resolution imaging in that case. Did I get everything? I think so. Yeah. All right. So I think Niccoló now will share his slides, and you can hear a little bit about the new development.
Thanks, Emil. Now we'll share my presentation. Okay. Okay. So, hi everyone. I am Niccoló, and I'm a development engineer at in-situ Chips, and I'm doing an industrial PhD at the Technical University of Denmark in Christian Mulheus group. In the first months of my PhD, I've been working on developing the Nano Channel Chip with new features. In particular, I have added nanofluidic traps in the chip in the imaging area so that it's possible to trap nanoparticles during liquid cell TM experiments. And this is the topic of this presentation. So we'll start talking about imaging nanoparticles in the liquid cell TM. As you know, liquid cell TM enables imaging of nanoparticles in a liquid media, and this provides several advantages. First of all, it's possible to observe in situ dynamics of nanoparticles moving in the liquids and the reactions occurring at the surface of the nanoparticles. It's also possible to observe in situ nucleation of nanoparticles, for example, by mixing two different solutions. And it's possible to observe the nanoparticles without the risk of modifying the structure, because when you observe a nanoparticle in the TM on a copper grid, you have to evaporate the liquid, and in some cases the sample could be modified by the evaporation process. So liquid cell TM is for sure very interesting for imaging nanoparticles. However, there are still some challenges. The most important challenge is controlling the liquid thickness. Controlling the liquid thickness is strictly related with the resolution that you can get in the TM. And Emil has already talked about this challenge that has been overcome with the monolithic chip that we have started commercializing in 2022. So the Nano Channel Chip already overcome this problem because the thickness of the liquid is controlled. There are still some secondary challenges. For example, getting nanoparticles in the viewing area in a reliable way. What researchers are doing right now is to use highly concentrated solutions, and they rely on random sticking of the nanoparticles to the silicon nitride membrane. However, these two approaches can lead to some disadvantages. Highly concentrated solution can lead to clogging of the system, while relying on random sticking can lead to a non-representative population of the sample, because you can only observe the subpopulation of your sample that is sticking to the membrane. Here I show you the difference between the nanochannel in the Nano Channel Chip without traps, so the one that has already been commercialized for several years, and the new product, the Nano Channel Chip with traps that I have developed in the first months of my project. So on the left, you can see a nanochannel without any trap. So you can see that there is a liquid with a well-defined thickness, and there are the two thin silicon nitride membranes in orange in this scheme. You can see that the nanoparticles move along the nanochannel with the liquid flow, and just a few of them can be imaged, and those are the ones that stick to the membrane. However, as I said, this is a random process. On the right, you can see how the trap works. The trap consists in a different thickness of the nanochannel in the trap area. In particular, the thickness is lower than the dimension of the nanoparticles. So when the liquid goes through the nanochannel and moves the nanoparticles with it, when it reaches when the nanoparticles reach the trap, they cannot continue moving along the nanochannel because the dimension is too big. So the liquid can pass through the nanochannel to the nanofluidic trap and reach the outlet, while the nanoparticles are confined. It's important to stress that this confinement is a physical trapping method, so you don't have to change the surface chemistry of your sample. This trapping solved the two problems that I've mentioned earlier, so you don't have to rely anymore on random sticking, and there's no need to use highly concentrated solution. So it's possible to use to perform single nanoparticle studies by using very low concentrated solutions. We have started testing two designs. They both rely on the same principle that I've mentioned earlier, and we're already working on other designs. In principle, we can do custom designs depending on the user needs. But these two are the ones that we have tested so far. The first design is called straight channels design. It's a very simple design. There are several parallel nanochannels with a constant width, in this case 2 micrometers, and the traps are along the y direction. So now I will use my pointer. Okay, as you can see here, what looks like a nanochannel with a non-continuous nanochannel, it's actually a nanochannel with a trap in between. At higher magnification at the optical microscope, it's possible to see the traps, and in particular, they are very clear on the TM, and you will see that later in the TM images. So, as I said, the trap is on the y direction, along the y-axis in this case. Moving to the Richten design, here the design is a bit more complex because we have two different kinds of nanochannels. We have the inlet nanochannels and the outlet nanochannels. So the inlet nanochannels are defined as the nanochannels on the inlet side of the imaging window. So imagine that the inlet is on the top side. All these channels that are starting from the top side are the inlet nanochannels, while the ones at the bottom are the outlet nanochannels. The width of the these nanochannels is 5 micrometers at the beginning, and then it goes down to 0. The inlet nanochannels and the outlet nanochannels are connected through 14 trapping channels. So in this case, the nanofluidic traps are along the x direction. So the liquid goes through the inlet nanochannel. The nanoparticles are confined in the inlet nanochannels, and then only the liquid can move to the outlet nanochannel and reach the outlet of the system. Here I also show you a scheme of the section so that it's more clear. So considering the straight channel design, I took a section along the y-axis, and as you can see, imagine that the inlet is on the top side. Here we have the inlet side where the nanoparticles come from with the solution. Then at the middle, there is this nanofluidic trap with a lower thickness. The nanoparticles cannot continue. And then there is the outlet side where there are no nanoparticles because they are confined. The Richten design is different. So in this case, I took a section on the along the x direction. Here you can see the inlet nanochannel. So here, with the nanoparticles that are confined, and then the trap along the x direction. In the outlet nanochannel, as I said, you don't see any particles because they are confined in the inlet nanochannel. Now I will move to the results of the results to obtain with the TM. But first, I will show you a video of the drop casting of the sample, just to show you how easy it is to perform an experiment with this chip. So here there is a chip in the gel box. We use a pipette and we drop cast a droplet, and as you can see from one inlet, and as you can see, the liquid is filling the bypass microchannels, and then it fills the nanochannels. Then you can mount the chip on the inside chips holder, and you're ready for your experiment. Okay, here I will show you the trapping dynamic using a Richten design. So after watching this video, everything I said earlier will be more clear. Now you can see the dry channels, so there's no liquid. And then the top side, we have the inlet side, while at the bottom, we have the outlet side. Now you saw the liquid coming from the inlet side that instantaneously fill the inlet nanochannels. Differently, the outlet nanochannels are filled more slowly. I can go back so you can see. For example, here, they are filled more slowly because the liquid has to pass through the trap channels. So since the liquid thickness is very thin in the traps, the fluidic resistance is higher, and so it takes more time to fill the outlet nanochannels. In this experiment, we used gold nanoparticles, 10 nanometer particles, and now I will show you that the nanoparticles are trapped in the inlet nanochannels. So starting from this video, okay, here you can see an outlet nanochannel, and there are no nanoparticles here. Then we move to the trap region. You don't see nanoparticles. You see some nanoparticles in the first part of the trap region, but then you see the majority of nanoparticles in the inlet channel. This is the inlet channel. So as you can see, the nanoparticles are confined. In this case, you can also see a few nanoparticles in the first part of the trap. But the reason why is that the sample here is 10 nanometer in diameter, and the thickness of the traps for this chip is 15 nanometers. So in this case, the nanoparticles are still slightly smaller than the trap. However, since the liquid thickness is so small, the probability of the nanoparticles sticking to the membrane is so high that they are still trapped, but in the trap region. Here you can observe, for example, the self-assembly of these nanoparticles in the inlet nanochannel. And you can, for example, compare the different dynamics in the region with a very thin liquid and in the region with a proper nanochannel with 150 nanometer in thickness. Then we can move to the other design. So here I'm showing you the straight channel design. In this case, we tested the chip with silica nanoparticles, and the dimension is 50 nanometers. So in this case, as you can see, there are no. This is the one that I'm pointing is the trap region, and this is the nanochannel. As you can see, there are no nanoparticles in the trap region because in this case, the nanoparticles are bigger than the trap. So here it's very clear how the trap works, and you see only nanoparticles here. After a few minutes, it's possible to observe the amount of nanoparticles trapped here. You can observe again the dynamics and how they self-assembly at the trap. Here we observe the self-assembly of gold patch nanoparticles. In particular, in this case, the particles are gold cuboctahedra with 55 nanometers in edge length. We obtained these images in collaboration with the Tianchen group from University of Illinois. In this case, we drop casted the solution as I showed you in the video earlier. And you can clearly see in this image, I will just use the pointer, in this image, how like the nanoparticles are trapped in the inlet nanochannel. So here you have the inlet nanochannel, here you have the trap channel, there are no nanoparticles here, and here you can see part of the outlet nanochannel that is clearly empty. There's just liquid, and you can see that by the different contrast with the membrane. So in the video, it's possible to study the dynamics of self-assembly, and in these images, you can also study the combination of superlattice in a different orientation. Here we show another experiment. This is a reaction, it's a galvanic replacement of gold. And these images have been taken by Parivash Moradifar and Emil McKeown-Green from Stanford University. The sample is consists of gold nanorods, 30 nanometers wide and 80 nanometers long. Again, the sample has been drop casted, and then you can observe in this STEM image the sample confined in the inlet nanochannel. Then thanks to the traps, we can exchange the liquids because we are sure that the particles are not going to be moved out from the imaging view because they are confined. So we insert a solution with palladium, and we can observe the galvanic replacement of gold. So what happens is that palladium replaces gold in the nanorods due to the different reduction potential of palladium and gold. Here you can see the reaction occurring, and you can observe these shells around the gold nanorods. Earlier, someone asked about proteins, and we also have some results, in this case with ferritin nanoparticles. Ferritin nanoparticles are 12 nanometer in diameter, so they are very small. And in this case, the nanofluidic trap is 15 nanometers. So as I mentioned earlier, you can also trap some nanoparticles in the trap region. However, as you can see, the majority of nanoparticles are trapped in the nanochannel. These images have been taken by Murat Yezibolati from the Technical University of Denmark. And here you can see another image at higher resolution of the nanoparticles. With this, I have concluded my presentation. Thank you for your attention. And of course, I would be glad to answer any questions. And also, if you want to ask any questions in person, I will be at M&M 2025 with Emil. We will have a stand there. And we also have a poster. So a poster about trapping nanoparticles. So if you're interested, you can see the date and the time, and you can just come and ask any question that you have. Thank you.
Yeah, we are almost coming to an end, and we have just one more question, this time from Giuseppe. And he asked, do you somewhere provide specific details regarding how the nanochannel designs was developed with respect to its hydrodynamic properties? And the very brief answer is no, because we have moved forward with our designs extremely qualitatively, very experimentally, and based on our observations in the microscopes. I will say something interesting that we have also talked about, Giuseppe, is incorporating COMSOL simulations in the future to see how at least we can simulate some of this flow behavior in the channels. So that's something in the future to come, and hopefully we will get really good at that as well. And if there are no further questions, then I just want to say a big thank you to everyone who signed in. That was fun to do this first webinar, and we are going to do more. So stay tuned for that. We are planning around every second month from now on, we'll have a new topic to discuss, and we plan to be inviting customers of ours that have published, and also researchers that we work with who have great results. So hopefully we can keep on having these webinars and sharing new insights and new discoveries using our chips. So that's it for now. Thank you so much for signing in. See you next time.